Today we talk about these two expressions, x to the fourth plus 64 and x to the fourth plus x cubed plus x squared plus x plus 1. Both of these have something in common. If you plot them, they're both U-shaped and never cross the x-axis. No real roots does not imply no factors. How do you tackle them? Give you a hint. One of these can be factored into two smaller polynomials with integer coefficients. The other is impossible to factorize. Which is which? Let's start with x to the fourth plus 64. Most people call this impossible to factorize because it's a sum of squares. But we can factor it by completing a perfect square. To turn this into a perfect square, we need a middle term. Remember the square of a sum formula. Our a squared is x squared squared, and our b squared is 8 squared. So the middle term we need is 2 times x squared times 8, which is 16x squared. The technique is to add 16x squared and then immediately subtract it to keep the expression balanced. Now these first three terms are a perfect square, x squared plus 8 all squared. And we're still subtracting 16x squared, which is 4x squared. This is a difference of squares. We can split it into a minus b times a plus b. Reordering the terms, we get x squared minus 4x plus 8 and x squared plus 4x plus 8. We factored it. This is called the Sophie Germain identity. Now consider the second one, x to the fourth plus x cubed plus x squared plus x plus 1. If you try grouping or other standard factoring techniques, you will find no factors with integer coefficients. But failing to find a factor is not a formal proof that it's impossible. For that, we need a more rigorous criterion. This is Eisenstein's criterion. It is a rigorous criterion for determining if a polynomial can be factorized. First, we look for a prime p that divides every coefficient except the leading one. Second, that same prime p must not divide the leading coefficient, which is usually 1. And third, p squared must not divide the constant term at the end. If all three check out, the polynomial cannot be factorized. It's that simple. Our polynomial is just all ones. No prime divides 1, so we're stuck again. Or are we? We can apply a substitution by replacing x with y plus 1. If the substituted version cannot be factorized, the original cannot be factorized as well. We can expand this using the binomial theorem, but there's a shortcut. This sum is a geometric series. So f of y plus 1 is just the quantity y plus 1 to the fifth minus 1, all over y plus 1 minus 1. If we expand the top, the ones cancel out. Dividing by y, we get y to the fourth plus 5y cubed plus 10y squared plus 10y plus 5. Now look at that prime p equals 5. Does 5 divide 5, 10, 10, and 5? Yes. Does 5 divide the first coefficient 1? No. And finally, does 5 squared, which is 25, divide the last term 5? No. By Eisenstein's criterion, this shifted polynomial cannot be factorized, which means the original expression is also impossible to factorize. So, x to the fourth plus 64 is a factorable polynomial, while the second expression is impossible to factorize. Before we go, here's a challenge. Can you determine which of these two can be factorized? What do you think about this video? Leave your answer and feedback in the comments.